Okay, welcome again. The topic of this lecture is medium-term morphodynamic area models, now MTM area models. So what do we mean by that? And it's also wave averaged. Let me first give you an overview of what it looks like, a model like that. So the setup is you can see in these nice colored icons. So process-based modeling, which means that we resolve the individual processes, but in 2 dimensions. And it's an approach used in Delft3D and XBeach, but also in Mike 21 or Telemac, other models. You start with a bathymetry or bottom depth. As you see here, there's a nice tidal inlet. Based on this bathymetry, you can do wave simulations and current simulations. And these two interact with each other. The waves impact the current and the water levels impact the waves. And together, they create a sediment transport pattern that varies with the tide and with wave conditions. And that leads to bottom changes. And well, in the old days, we would stick to that, but nowadays we look back and you see the bottom changes feed back into the bottom depth, and that influences the waves and the currents in the sediment transport. And in an endless loop, we continue this. So we simulate the basic processes and we use an upscaling approach where we keep looping this and hopefully end up at large timescales. And this looks, for instance, like this. Here we have a tidal current. This is the Eierlandse Gat, north of the island of Texel, where a dam was built in the late 1990s to combat the erosion of this bit of the coast. And actually things happened there that were not predicted at all. And so a lot of study was done afterwards to understand better what happened. So this is the tidal, let me play this once again, the tidal current. And what you see here is also along the coast, you see these wave-driven currents. They can even go in the opposite direction as the tidal current. Now, waves are, we describe the evolution of the wave energy. What you see here is the wave energy flux. During high water, you have much more propagation of waves than during low water. Let's play that again. So we're approaching low water now, and you see that the ebb shoals here dissipate a lot of the wave energy, but also the currents impact the propagation of the waves. And this then denotes the sediment transport pattern, where you notice high concentrations and transports along the coast due to the wave-driven longshore current, but also, of course, where you have major tidal currents, then there's a very dynamic area and high transports, and particularly also around this groin, or this long dam is 400 meters long. That has a big impact on the current patterns and the transport. And finally, we see the bathymetry moving. Here you see the channels and the ebb shoals move back and forth with the tide. This is, of course, a bit exaggerated. In reality, it doesn't move that much within a tidal cycle. This is part of the effect of the morphological acceleration that we are applying here. But let's go to the basics of what is in these models. First of all, the main equation here is the bed evolution, where ZB The epsilon p is the porosity, the ZB is the bed level, Sx is the transport in x direction, is y the transport in the y direction. We can have a term for the subsidence of the soil, and we can have sources in the form of nourishment or dumping and erosion or dredging. The sediment transport that was in this equation is built up of a component that goes with the current times the concentration vertical. So we can it's a double integral of the velocity times the concentration averaged over the time and integrated over the from the bottom to the surface. Now the question is, which flow velocity do we take into account here? Do we take the tide, orbital velocity, turbulence? Other questions are, what kind of sediment are we talking about? Sand, silt, or mud? They respond in different ways. And how does the sediment transport in the end respond to bottom changes? And that is the most important aspect in determining the dynamic behavior of the bathymetry. So we'll go a little bit through a number of the processes and their formulations for tidal currents, wind-driven currents, waves, wave-driven currents, sediment transport, and bottom changes. First of all, the flow, we use the momentum balance or shallow water equations where we have terms inertia, the advection terms, how is the momentum advected by the current itself, the Coriolis effect, Fv and Fu, due to the rotation of the Earth. We have the water level gradients or the pressure gradients. We have external forcing, for instance, by waves or by wind. We have mixing, horizontal Reynolds stress, and in the end, all this motion is reduced or counteracted by bed friction, bed shear stress. The continuity equation, we have zeta we use here, or Zs. The water level varies in time as a function of the gradients in the discharge. And discharge, local discharge, is the water depth, in this case positive downwards, plus the water level, that's the total water depth, times the velocity in the u direction, in the x direction, and the velocity in the v direction. And we can have a source or sink in terms of pumping, or in a course model we might include the discharge of a river as a source. If you look at an example for the tidal alongshore current, that is mainly driven by so we have an inertia term, which is important in deeper water. We have a bit of an advection term, but mostly it's in shallow water, it's the longshore gradient that is balanced by the bed shear stress. And this longshore gradient is big if you have a tidal current that doesn't go too fast along the coast in shallow seas. So for the Dutch coast, typically we have something like 0.5 meter per second tidal currents. And I'll show this again. You see that these tidal currents are mostly parallel to the shore. Now, another important forcing is the wind. And in the coastal systems lectures, we've gone over the wind-driven longshore current. It's very easy to understand that the same, well, shallow water equations here, we can select just three terms: the inertia term, and the wind shear stress, and the bed shear stress that are in the equilibrium situation. You have a balance between the wind shear stress and the bed shear stress, and in the beginning there's no bed shear stress yet because the velocities are small, and then you have a sort of linear increase of the velocity with the wind shear stress. So equilibrium situation is that the bed shear stress rho CFU squared equals the wind shear stress. So you should end up with a completely uniform velocity field if CF is constant. But these curves show that in shallow water you have a very rapid response of the wind-driven current, but in deep water it takes much longer to accelerate. And of course, if we combine these tide and wind-driven currents, and we can get to a situation if we have a strong southwesterly wind in this case, that we end up in a situation where the ebb current is sort of blown away by the wind-driven current. The wind-driven current can be strong enough to suppress the tidal current. Now, the next component is the wave modeling, for which we use the model SWAN, which is based on the Eulerian spectral energy balance, which considers that the total wave energy is built up of packages of wave energy that have different frequency and different direction, frequency f and direction theta. And there is propagation in there's a rate of change in time. There's a propagation in the horizontal directions x and y, and there's also propagation in the theta direction, so which means refraction. The waves are turning towards the coast, and of course, if we look at larger areas, then we also need to consider the propagation in the frequency direction, but we can largely ignore that in the coastal zone. These S, that is in larger scale model, that is the wind growth and nonlinear interactions. But for us in the coastal area, the most important thing is the sink term because of wave dissipation due to braking and to bottom friction. So again, advection, refraction, and sources. An example of the importance of refraction and how well a model like SWAN can represent that is Scripps Canyon in the United States on the west coast, south of California, where you have here a very deep canyon. This is the depth positive down. So you have this deep canyon with the two branches towards the coast. And there's been a large measurement campaign called NSEX to verify various wave models. And here you see an example of the large-scale wave distribution. So waves given here in deep water. And what you see is that along these canyons, the waves are refracted away from the canyon, away from the canyon. and that leads to, at the end of the canyon, relatively low wave heights, whereas a bit away from the canyon you have rather high wave heights. And for instance, in this case, these are famous surfing beaches because they always have relatively high waves because of this refraction effect. So more about the swan and wave modeling in the lecture about the regional models in swan. But now let's turn to wave-driven currents. Let's start with the simple case of longshore uniform wave-driven currents. In that case, in the cross-shore direction, we have a balance between, well, there's these other terms that are in the longshore uniform sense not so important. But here we have, for instance, the cross-shore water level gradient, eta the water level, and s the cross-shore coordinate, and this balances with the cross-shore wave forcing, which would be one of the outputs from a model like SWAN. In the longshore direction, we have a balance between the inertia term, the acceleration of the longshore velocity, the un in n is the longshore direction in this case, and we have a longshore water level gradient. Usually, if it's just wave-driven current, it's zero, but it can be a tidally driven gradient, and then it's not zero, it's varying in time. We have the longshore component of the wave force, and ultimately the wave-driven current is balanced, the forcing is balanced by the bed shear stress. Now, if we simplify this, just write these terms. So we have the balance between the cross-shore wave force and the setup gradient, and we have the longshore acceleration that is balanced by a possible tidal gradient, and otherwise the wave force and the bed shear stress. And if those two are balancing, then we get a wave-driven current that is, of course, mostly active in the the surf zone, because out of the surf zone, the wave-driven forces are practically zero. And the colors here indicate the water level, and that is the result of this equation that determines the wave setup. Now, this is a very nice picture with in a two-dimensional model. It's actually this size, this two-dimensional model. And you see that it is a very nice uniform solution because the bathymetry is uniform here, the wave boundary condition also. But in practice, if you don't do something special, you would often see some sort of disturbed pattern, and that is to do with the boundary conditions, especially these lateral boundaries. It can give a major problem. For instance, if you impose a water level that doesn't include the wave setup, and well, you might not know the wave setup before you do the simulation, then inside the model you get the wave setup, but at the boundary you specify zero. So what you get is a gradient from here to the boundary and from here to the boundary. So here the flow is accelerated too much, and here the flow is actually reversing. You can imagine if you put a flow pattern like this into a morphological model, you get huge disturbances at the boundary. Now, on the other hand, if we don't impose the water level, but the water level gradient, we've seen, we can assume that this water level gradient is something really large scale that is just reacting to the tidal motion at very large scales. and so it's uniform in cross-shore direction. And if you impose just that longshore water level gradient, then the setup um, and the longshore current profile can develop freely and without disturbances. This busy slide here tries to explain this. So now I've go to the situation where we have a more full two-dimensional simulation, and the gray terms are just the terms that we cannot resolve at the boundaries. And now you understand why I was using US and UN. S is along the boundary and N is across the boundary, but in a longshore direction. So these terms we have to neglect, but for the rest we can impose this d eta dn that you see here in the longshore current simulation. So by imposing this longshore gradient of the water level, we call this a so-called Neumann boundary, we can solve almost exactly the same equations at the boundary that we solve inside the model. And the only assumption is that the bathymetry and the flow patterns and so on are uniform along shore near that boundary. Now, with that kind of boundary conditions, we can create relatively small coastal models that are easy to set up and that can do so we don't have to have a huge area to cover for our model if we just want to simulate a small coastal structure, for instance.